Hello and welcome to everyone to our 41st session of the Porous Media Tea Time Talk. We are happy to have you here once again. And today, as usual, we are hosting two speakers from the young academy all over the world of the Porous Media community. And they will present each one a short topic about their current research. And so please, if you're interested, you're open at the end of each presentation to make your question. And we will take care of this session. And so today we'll have Sangli that for the first time will manage the session together. So also make a warm welcome to Sangli. But also we have a veteran of the channel like Nara and Marcel. And also there is me, Federico, that I will host the session for today. The speaker for today, before starting, I would like to remind you to put a like and subscribe to our channel. And also please click on the ring bell so you will be kept updated for the next sessions that will be held more or less once a month. So today we have two speakers, as I was saying before, Supriya and Omid. We will start with Supriya Bhaskaran. So please give a warm welcome to Supriya. Supriya is a second year PhD student at the Otto von Guericke University in Magdeburg. And today she will talk about her current research about the Lattice Boltzmann modeling and microfluidic experiments of the anode porous transport layer of water electrolyzers. So Supriya, welcome again, and please, you can start.
Thank you very much for the introduction. Maybe I will just put it to the full screen. Yeah, I think it's now clear. Yeah, thank you very much for your introduction, and thank you very much for giving me this opportunity to give a short overview of my research and my PhD at the Interpor Academy. So today I will be presenting on the study of two-phase flow inside the anodic porous transport layer of PEM electrolyzers using Lattice Boltzmann model as well as the microfluidic experiment. So before going into the topic, so I would give a brief introduction to our labs at the university as well as at the Max Planck Institute. So we have our own 3D imaging using the micro-CT facility where we can go to a resolution of 2 micrometers. And also we do Poe network and Lattice Boltzmann models for mass transport and heat transfer in porous materials. And at the Max Planck, we have our own macro scale electrochemical processes where we deal with our fuel cells and electrolyzers, and we also do experimental analysis, which is later used for validation of our macro, micro, and different scale modeling techniques. So today I would give a brief introduction about the PEM water electrolyzer because it's a new topic for the porous materials. And then I would also introduce the multi-scale modeling approaches and then a brief overview of the Lattice Boltzmann model and also our experimental setup on the PEM water electrolyzer cell, which is made from the microfluidic devices. And then we have our flow conditions and experimental parameters, and then summary and outlook. So what is basically the PEM water electrolyzer? So usually in the PEM water electrolyzer, we have two different sections. That's the anode and the cathode. So in the anode, again, we have our bipolar plates where we have our water that's flowing, and we have our porous transport layer that's mentioned as PTL. And then we have our anode catalyst layer. And then moving through the cathode, again, we have our cathode layer and again, a porous transport layer at the cathode side and also the bipolar plates. So majorly at the anode, we have the water splitting reaction where we get the hydrogen ions, the oxygen molecules. And in the cathode, these hydrogen ions react with the electrons and give the hydrogen as gas. So basically, at the anode, we have the water that's required for the reaction flowing across through the PTL and reacting at the catalyst, and we have the oxygen that's being removed at the same site in the anode porous transport layer and through the flow channels to the out. So this makes the complex process happening at the anode, where we have a countercurrent flow of water and oxygen. And that's why we have different problems. That's the like we can't operate our at high current densities, and there are significant voltage losses. And this also leads to a mass transport loss through the porous transport layer. So how this porous transport layer actually looks like. So here we deal with the titanium felt PTR, where you have these fibers which run through and you have a porous space. So this material is approximately with a thickness of 0.8 mm. So here I would be talking about how we determine the mass transport losses, combining the experimental and the multi-phase modeling approaches. So here we have like different approaches at different scales, starting with the lattice Boltzmann model, where you can see the yellow region, which usually takes a very small number of pores. For example, we say we just consider 100 pores in the lattice Boltzmann model. And then we could study the invasion physics and also the invasion pattern and threshold pressure at each pores. And then later we move towards the pore network model, which is conceptually represented as pores and throats, like here as shown in the figure. And then here you could see like the pink region where we could consider more number of pores. So for example, if we consider 100 pores in lattice Boltzmann model, maybe in PNM we could consider 10,000 pores, which makes it much more faster. And we could also extract the macroscopic parameters like the permeability, which can later be used to a macro scale model, where we could then consider the entire system to know about the efficiency and other process parameters. So with this, how do we extract this porous structure? So we have the titanium felt PTL, which is bought from the Silatec, Germany. And then we do our in-house micro CT scans with a resolution of 3.9 micrometer. And as I said, the thickness is around 0.8 mm and the material porosity is around 80%. And then once we get the reconstructed data of this micro CT, we then do the binarization, where we divide into the solids and the pore space. So the black region represents the pore space and the white represents the solids. So once we have this differentiating between the solids and the pore space, we then go for the watershed transform, which we do it with our in-house code, but it is also possible with software such as ImageJ. So here basically we inscribe a sphere into the pore spaces and try to find the size of the pore space. So basically here we have the pore diameters, different pore diameters across the PTL structure. And this might vary if we go for a smaller cross section, or we could also see for different regions across the PTL structure. So what is basically the Lattice Boltzmann model? So Lattice Boltzmann model is a CFD tool which is recently used to simulate the single phase and multi-phase flows in pore structure. And the major advantage of the Lattice Boltzmann model is that it could incorporate the real scale pore geometry, and it also acts as a Navier-Stokes solver. And comparatively, it's kind of much faster than the normal CFD softwares that we use. So for example, here with the example, I show how the Lattice Boltzmann model works. So for here, we took a 2D slice of the 2D representation of the porous transport layer. So here the black represents the solids and the white represents the pore space. And then we assume a small catalyst layer which has only one active sites from which the oxygen is being evolved. So once the oxygen starts to evolve, it moves across the porous structure based upon the capillary pressures. So if you consider this solids and the pore space as an image, then we take 1 pixel is equal to one lattice node, and in across this one lattice node we have 9 different distribution of the particles. So this is basically called the particle distribution function. So that's how we have our lattice Boltzmann equation, where we have our particle distribution function distributed as a function of distance and time. So once we sum up all this particle distribution function, we get our macroscope quantity, that's density, and also the momentum. But in 2D, we consider, like, we have only x and y direction. We consider 9 different distribution. What happens if we have a 3D geometry or a 3D structure? So here we have a 3D structure, and here we go for 3 different directions, and so we have 19 different distributions that we actually deal with. And as usual, as shown in the 2D, we also kind of assume some injection points across the bottom surface to be the catalyst layer from where the oxygen is being evolved. So here, for example, so we took a small cross section of the PTL, and then we try to keep the injection points, that's the white points, across the bottom surface from which the oxygen is being evolved. So, and then we had our comparison based on 3 different thicknesses that's being cropped from the original PTL structure. So starting with 0.2 mm, 0.5 mm, and 0.8 mm. So here you could see the distribution across the PTL, that's the oxygen distribution. It's kind of having a similar pattern when we have the same part of the PTL. So with this, we could know how the oxygen is flowing across the PTL structure. And now I will give a brief overview about the experimental setup. So basically we have our microfluidic device, which has an anode and the cathode side. In the anode, we represent the porous structures as pores and throats. It's not a real representation of the PTL, but since it's a prototype, we would like to start with a more simpler structure. So we represented our anode side as pores and throats. And the entire setup is made up of PMMA material. And here we use the anode catalyst as iridium ruthenium oxide, and we also have a cathode catalyst, which is the carbon supported platinum. And also, as I mentioned in my first slide, that since the complex is on the anode, we have a structure on the anode, whereas cathode, we don't much concentrate on the cathode side. So here, this anode, we have it represented like here, how it looks in the actual, in real. And then once we activate the reaction with the potentiostat, we have the oxygen being evolved from the catalyst layer. So the white here mentions the water and the gas, which is flowing from the bottom to the top. And we could also see it being removed by the flow of water, and also we could again see some refilling of the water that's taking place. So this makes sure that even though the catalyst layer is completely blocked with oxygen, we have some kind of water that's flowing into the system through either through films, or we have kind of support from the cathode side based upon the drag forces that pulls the water, that takes the water from the cathode side. So this is how we have this continuous process that's been taking place. So this process can now be differentiated into the drainage and filling cycles. So the drainage is the removal of the water out of the system, and we have the oxygen that's being flowing across. And then we have the filling, where we again, the water fills the system, and then we have again have the oxygen reaction that's taking place. So this is a continuous process of drainage and filling cycles. So the same, if we go for a higher current density and for a higher flow rate of water, and we could see more amount of oxygen being removed out of the system, and we have more amount of water in the system, which makes the reaction to happen again and again, and then we have more amount of hydrogen which is being produced. So with this, we could also calculate the electrochemical characteristics. So here we have, for example, at different current densities, we have a different voltage fluctuations. But when you see the mass transport over potential, it's kind of more than the usual water electrolyzer cell which is being operated. So this shows that there is inefficient supply of water to the membrane, which leads to drying out of the membrane. So this significantly reduces the performance of the electrolyzer cell. So with this, I would conclude with a short summary. So with LBM, we could have an in-depth analysis of the invasion physics that's happening in the porous transport layer. And we could also say the local injection points that may change the saturation profiles across the PTL. And in the experiment, we could see the invasion process and how it depends upon the rate of water and the current density. And also, we could see the entire porous transport layer or the network is not saturated by water, but it keeps the cycle going on. So, our next future work would be to directly incorporate the impact of catalyst layer into the PTL and to investigate based upon the Lattice Boltzmann model. And also in the experimental approach, we want to make the structure to be much more complex and to be much more representative, and then to quantify how the invasion occurs based upon different current density and flow rates. So with this, I thank again for having your attention during my presentation.
All right. Thank you, Supriya, for the very interesting talk. And I always be amazed to see a researcher who combines numerical analysis with both experimental. I think that's really a nice thing to do. So do we have any question on the chat? I don't think I see it now, but
I have one. We don't have on the chat yet. Maybe I could start with one. It's very nice. Supriya, really agree with Singh. It's both these things are very hard to do it by themselves, right? To do it both, as one single person, that's a lot of work. Just a detail on the experiment. So you said that this is a PMMA cell, right? The cubes, the little cubes that you have there that make the porous matrix, are they also PMMA? Is this like etched?
Yes.
So the whole thing is etched, right?
It's kind of mission etched. So basically, we have two different PMMA materials, like on top of each other, and in the one we try to mission it to make the structure. It's kind of hollow with 2 mm thickness, and then we keep another PMMA material on the top, so it's transparent and we could see what's happening inside the structure.
But then you don't have problems with like water going like in between these little cubes and the top.
Yes, we had this leakage problems, but based upon the sandwiching, we tried to compress it as much as possible, and then we were able to resolve this. Yes, we had all these problems, leakage at different levels. When we go for higher flow rate, yes, due to pressure, there was a lot of leakage. Yes.
We have one question on the chat from Ramon. So the question is, hi, thank you for your presentation. Can you talk more about the choosing of the multi-phase Lattice Boltzmann model you used? Was it pseudo-potential, free energy, colored model?
No, it was the multi-phase Lattice Boltzmann model. Yeah, this is the model which I'm using right now.
I think we may have question for one more question. While the audience in the online may thinking of the question, I also have one question. So when you showed your Lattice Boltzmann model simulation data with different thickness of the transport layer, you showed depth versus oxygen saturation percentage. Yeah, this one. And then I was expecting that this trend will be linear, like high from the inlet and then decreasing as you go up further. But it seems very a non-linear trend, like high in the beginning and then decreasing and then increasing. Do you think that's due to the artifact coming from the size of the simulations volume, or what do you think that's the cause?
So actually I didn't go in depth about the PTL structure because I didn't want to make it complex. But yeah, this porous structure itself is a graded one, where we have a small pores at the bottom and kind of bigger pores on the top. So this fluctuation in the saturation profile is basically because of the pores that's being invaded. So when we have a smaller pore, then we have kind of a lesser saturation, but we kind of go up and up. Sometimes the bigger pore gets more amount of volume, so it's more. And then across the end, as you say, it's low. So whenever it's on the top, it's always a low saturation. So it's basically because of the pore geometries that we have.
I see. All right. I think it's time for us to move on. Thank you again,
Yeah,
Supriya.
thank you again. Yes, thank you so much.
So our next speaker is Omidreza. He is a researcher and PhD student with a focus on digital rock physics and special core analysis at the Reservoir Engineering Chair of Montanuniversität in Leoben. And his contribution to the project goes more into the direction of simulation and software development. He has a background in petroleum reservoir engineering, and originally he's from Iran. And welcome, Omidreza, and the floor is yours.
So thank you very much. Thanks for the introduction. Hello, everyone. Thanks for joining the talk, and thank you to the Porous Media Tea Time talk team for organizing the event. So I just quickly share my screen. Okay. So do you see the presentation?
Yes, we do. It's great.
Okay. Perfect. Good. So yeah, as the title suggests, we are going to talk about digital rock physics to stochastic reservoir modeling, which is also the title of the project which I'm working on. So I would like to start with a bit of a fundamentals about relative permeability and capillary pressure. So these functions are key uncertainties for displacement in multi-phase flow, yeah? And they must be measured at a great expense for different applications like oil and gas production, CO2 storage, and geothermal reservoirs. But there are some concerns and limitations which limits our measurements. For example, the conventional methods which are used for the to measure these functions, they are usually taking a lot of time, they are expensive, and if you have many rock types which you would like to analyze, which is usually the case, you are limited by your budget and the time that you can spend on these measurements. And this gets worse for the case that you have heterogeneous reservoirs where you need more samples, so to get more data, and usually then because you don't have this number of samples, then you lack statistical also variations for your results and calculations, which is needed right now for modern simulation approaches which have a stochastic approach and need any stochastic input. And also when we do this kind of measurements, these functions, they are usually derived phenomenologically, which means there are gaps in the fundamental understanding. So what we are trying to do is to bring in a more fundamental understanding of multi-phase flow in porous media by combining both the conventional and fundamental methods and quantifying the uncertainties and sensitivities of these functions to different parameters. So starting from the moving on to the methods of measurements, the first one and the conventional one to calculate the KR and PC functions are SCAL, which stands for special core analysis, in which you have, for example, a steady state experiment here, where you flow at different fractional flow. When you flow or inject the core to occur 2 phases at different fractional flows, and then measure the production or saturation and the pressure to calculate the relative permeability, and a centrifuge in which you rotate the sample at different rotations to calculate the capillary pressure for your sample. Usually the samples here are about 5 centimeters long, and you assume that your sample is homogeneous, and to be able to satisfy your assumptions of the formulas that you would like to use. And these experiments, as I said before, they are expensive and they take a lot of time, so they do not let you easily have a statistical description of your rock type. So with the new methods of measurements, so we have porous scale modeling, which uses a more fundamental set of formulas to calculate the relative permeability and capillary pressure. But here we are dealing with a very small sample. Yeah? So there are this can be relatively cheap and fast, but the problem is the information that you get from a small sample, which can be not applicable to a larger sample or the rock. Yeah. There are different approaches here. One can be pore network modeling, as we had in the previous talk, or the direct simulations, which is done with morphological methods, which has both positives and negatives. With the direct method, you are more accurate, but it's more computationally expensive. With the PNM or pore network, you lose a bit of a prediction capabilities, but you are faster. So this is one end of the scale. If you move to a smaller scale, on the other hand, if you want to capture more properties of your rock, if you want to characterize heterogeneity, you can go to a larger sample. You can do the experiment in your simulation on, for example, samples of 15 centimeters and longer, and here you can try to capture your heterogeneities. But then on the end, this is taking a lot of time, both for experiment and the simulation from you. Yeah. So what we have done until now or what you can see here is the interpretation of the scale measurements for stelliodis carbonate. So you see the uncertainty range for the different sample variations here. We will move through how we came up with this calculation later, but the point that I want to emphasize here is that if we use the same set of calculations that we have from a scale and try to predict the measurements that we have from the long core, we see that there is a large gap here in the between the predictions and the experimental measurements, about 50%, even though that we are using the same fluid pair, and then you are on this using the same rock type. If you try to calculate the relative permeabilities from the pore network or pore scale modeling, then you're also a bit off from what you have from scale calculations. So we have, as you can see here, we have a data integration problem once you move between different scales, from pore scale modeling to the long core analysis, which can also go further to the full field development if you are taking the calculations that you have with these methods. As we said in the beginning, this can be also used for CO2 storage applications. But here we see if you change your fluid pair to CO2, then on the right side you see that this difference with your the difference of prediction with your experimental measurements get larger, which is 66% compared to the 50 that we had before, and this adds on the top of the problem. So what we have done to try to develop a workflow which you can in the end try to implement for your upscaling approaches. First, we started with a scale. So we said here the analytical solutions are not perfect because of the assumptions that they have. Then the predictive capabilities, they are limited. So we developed this workflow where you can simultaneously history match all your experiments together, so both the centrifuge and the steady state that you have, starting from analytical solutions and then putting it in a simulator. You might be also limited by the parameterizations that you have, like Corey, the famous ones like Corey and LET. And then here we came up with a point-by-point approach to represent your relative permeability to not be limited to the parameterizations. And in the end, we characterize the uncertainty range using Monte Carlo methods. And the results is what you can see on the left side. This is what we discussed, where you can have uncertainty ranges both for capillary pressure, relative permeability, and see how do they lie on the top for different sample-to-sample variations, and so on. Yeah. So what we have done here is also is a part of the MRST package. So this is open source. You can download it right now and give it a try for yourself. And the graphical user interface here that you see, this is what we use for our courses that we teach at the university. So coming back to the topic, the analytical solutions that we talked about, now here I show the problems with the analytical solutions that we talked about. Yeah, so for example, with the centrifuge at the top figure, you can see if you try to get your PC with these methods, you are off your measurements. This is the same with your pressure from the steady state or the saturations that you measure from the steady states if you do your interpretation in a sequence in a meaning that you first go for the first you for example use Darcy to get your relative permeability, and then the next one for the capillary pressure, and not combining them. So the next limitation can be the parameterizations, as we talked about. So here you can see if you use Corey, LET, the modified version of the Corey, you are still not able to completely capture or interpret your experimental measurements. And we solve this by using a point-by-point history matching, in which you see here at the bottom. Then you can have a complete interpretation of your experimental data and predict them in a best way possible. What we are planning for the future, is that once we have the ranges calculated from scale, so the uncertainties are quantified, we would like to see how we stand, how can we upscale this, right? So what is trending right now in the literature is the capillary pressure scaling methods. So this is also what we use here, and we see that using the capillary pressure scaling ones, we can capture the 1D saturation profile that we see in the long core experiment, but this is a 1D simulation where you do a 1D slicing of your core. So here we can also, because the simulation time is still in a reasonable time, then you can do a bit of optimization with genetic algorithms and things like this to see if you need to shift your KR and PC graphs. And then you can try to see how does this look like for the 3D core flooding simulations. And this can translate to the same case that you have for a full field, which you move on from simple assumptions to the 3D flow, which you should have in a full field case. Having said that, what we are doing here is the integration of the data from the small scale to the large scale. So we are trying to develop the workflow for this upscaling, plus the software development in an open source way, which is open to the community, and with an integrated software where you have like a graphical user interface for each step of the way, and then you can use the output of one to the input of the second one, and then see what are the implications of these ones as well for the case that you have production from a full field. Thank you very much for your attention, and I would be happy to answer any questions that you might have. And also thanks to my team for supporting me in this project.
Super, thank you very much, Omid. It's a very nice presentation. And so if there is any question from the chat, please type it in. And also for the studio here, I have a quick one. So you mentioned in the beginning, like this, the big difference, right, between the predictions and the experiments, and that you have like the workflow to try to overcome these things and then measure like the uncertainties properly and so on. Do you have any intuition or any feeling for what kind of scenario would lead to bigger errors between the experiments and the simulations? Is it like just guessing? Like, is it like if you have like a compressibility effects, then things get hard, or if one fluid is much more viscous than the other, then things get hard? Do you have any feeling for that?
So, so to be honest, the case that I'm showing here is the Lattice carbonate, which is a very heterogeneous case. So we are already going for the worst case. Yeah. So this is usually considered as the worst case scenario. This is like the hard case one. So I can imagine that if you have a rock type which is a bit easier to interpret, you should not have a difference like this. But to answer your question, here we are focusing just on the relative permeability and capillary pressure. So not going through the things like compressibility and things like this. In the sense of the just the relative permeability and capillary pressure. So of course this comes on things like how you construct your curves basically. Yeah. So what are your entry pressures, for example, for capillary pressure? What is your connate water saturation that you are assuming for your curves, and then parameters like this. You know, so these are the main factors that I would consider. Does this answer your question? Or?
That's yes. Super. Thank you. So do we have any other questions here from the studio or from the chat? I don't see it yet. So you have included your email there as well, right? That's the end slide. So the presentation stays in our channel, and then also if people want to contact, they're welcome to contact you after both speakers, of course. Okay, so if we don't have any more questions, I think we could finish this session here, and then thank again both speakers from today, Supriya and Omid there. And thank you very much for your presentations. And we move on to announcing the next session, which is the date and time is defined, is on the 13th of December. So that's 1 month from now. This is our last session for this year at 3:30 in the European time. The speakers are still going to be announced, but if you do like Federico said in the beginning, if you like, subscribe and hit the bell and do all the things that people do on YouTube these days, then you're going to get information about that when it comes. So thanks once again. And on behalf of the whole team, I would also like to thank our new member, Sung Lee, that is joining here today. So from the University of Minnesota. So we're happy to have some of the team members. There's a little bit of a rotation, some graduate and retire, and then some new ones come. I think that's very nice, very healthy for the functioning of our team, and that's been going very well. So thanks very much to the speakers and to the audience, and we'll see you again in 1 month from now. So bye-bye.